Good day and afternoon, everybody. So today we are just continuing with our second part of our introduction in metamorphic petrology. And that was it then so far. Then you can answer all the short questions from this chapter, let us say till Friday. And I will continue to on Wednesday to upload then at first a couple of classes dealing about igneous petrology, then more in detail as in the introduction, and then afterwards a couple of weeks long things related to metamorphic petrology, also more advanced as in this small introduction. Yeah. So we stopped last week with this slide, and now we are continuing just to the next one. So here we are starting today just with short questions for the last chapter. Then we have here the first question: how is lady cleavage related to tectonic forces? What force causes a mineral or minerals to align with one another? I showed you there in our last presentation or last two presentations a couple of examples how minerals becoming or showing a cleavage and becoming aligned with one another. Yeah. So then we have the next question: would you choose to rely on chemical composition or type of foliation to determine the metamorphic grade? First, and secondly, why? So now we are coming to point number 4 on this chapter in introduction into metamorphic petrology, and here number 4 deals about regional metamorphism and metamorphic grades. So we have a grade of metamorphism, yeah, and metamorphic reactions are always controlled by pressure and temperature. Then we are talking about low-grade metamorphism. We have intermediate metamorphism, and we are talking about high-grade metamorphism. And I introduced already what type of metamorphism is, or we understand under low-grade metamorphism, and what type of metamorphism is understood under high-grade metamorphism. And of course, intermediate metamorphism is then just located between low-grade metamorphism and high-grade metamorphism. So regional metamorphism and metamorphic grade. So we can subdivide an area using mineral isogrades. So within our zones of mineral isogrades, we have zones of changes in mineral chemistry of a rock assemblage, or even changes on the chemistry of a certain mineral. So, and index minerals are minerals, for example, like staurolite. They are formed under a certain pressure and temperature in a certain pressure and temperature window, or we can also say under certain pressure and temperature conditions. So then we have groups of 2 or 3 indicate minerals forming then an isograde. So and now I will show you an example of mineral isogrades and how they are formed and where they can apply it for. So here, for example, we have a map, yeah, from the east coast of the United States of America. In the northern part, you have Canada, yeah, below we have US, and there you have then also different shortcuts for the different states. So, but now we are not interested in the political states, we are interested in metamorphic isogrades. So, and now we have here a key, the inset here shows us a key. We have then this in the sand colored area, which is here classified as NY, yeah, for New York, I think so. That is not metamorphosed. So there we will not find any metamorphic rocks. So then we have this greenish area close to this sand brown area, and there we have the first zone, and that is a chloride zone. Yeah, here we have this light greenish zone here, yeah. Here we have this light greenish zone, and here we have also this light greenish zone, and that is a chloride zone. And you know, a chloride is formed under low pressure and temperature conditions under green schist facies conditions. So, and therefore we have the first zone. Then we are coming to the next zone here in bluish, yeah. So, and that is a biotite zone. And this biotite and chloride zone has been interpreted as a low-grade metamorphic zone. That means in such a low-grade metamorphic zone, low-grade metamorphism has been taken place. And low-grade metamorphism means we are dealing here with low pressure and low temperature metamorphism under green schist facies condition. And you know from last semester what are green schist facies conditions and which minerals we can find in green schists or green schist facies rocks. So then we have this brownish, light brown colored zone and dark brown colored zone. And that there we have a garnet zone. That means the crystal garnet occurs, and in this dark brown zone the mineral staurolite occurs. Yeah, and if we have garnet and staurolite, then we are talking about medium grade metamorphism. That is the intermediate metamorphism. We have intermediate temperatures and intermediate pressures, like we can find under blue, under amphibolite facies conditions. Yeah. So now we have here a staurolite inside. There we have a chloride inside, and in our high-grade mineral assemblage we have sillimanite inside. Yeah. That is now the next zone that is a little bit light greenish colored. Yes, and there we have then also some sillimanite, yeah. So in the sillimanite, you know this from our field trip, these are is a mineral which is formed under high temperature conditions, and therefore we are talking about high-grade metamorphic rocks. So now we have staurolite inside, we have sillimanite inside. If we have sillimanite inside, then we have a lot of aluminium in the system, and then most probably when I'm looking at these minerals, also staurolite, they are typical minerals found in aluminium-rich rocks, and aluminium-rich rocks, that is most commonly a metapelite. Yeah, that means we are dealing here with former sediments, and there we are talking about former aluminium-rich sediments. So, and then we are forming here, or we can form then sillimanite. And if we have then these different zones, we have then these isogrades. And if you remember your field trip there, we had there you discovered also isogrades, yeah, and the high grade metamorphic mineral assemblage, that was this one: sillimanite, garnet, cordierite, biotite. Yeah, that was this high grade metamorphic assemblage, and I think Sepiso was working in this group where they have worked on this high grade, or where they found the high grade metamorphic assemblage, where we had then these huge needles of sillimanite inside. So now we are going to the next slide. So here we have again a definition: indicate index minerals define metamorphic zones. Yeah, that is actually just repeating from that what you have learned last year in the field trip. Isogrades can be used to plot the level or degree of metamorphism. You know this also from the last year field trip. So now we have here again such a PT diagram. On the x-axis we have the temperature, on the y-axis on the left side the pressure. Unfortunately, the pressure increases from the bottom, from the top to the bottom, as the same here for the depth, yeah. So that is the opposite as I have showed to you last semester using the metamorphic phases diagram after Escolar. Now this order has flipped it, but anyway, you can flip it in your brain again. So then we have here low-grade metamorphic rocks, and there we have slates and phylites. Yeah, we have already discussed this. We are increasing the metamorphic grade, and we are forming intermediate metamorphic rocks. These are schists, yeah, and blue schists. Yeah, blue schists, you can find them typically under blue schist phasous conditions, yeah. And later on we have high-grade metamorphic rocks, and these are gneisses, yeah, and migmatites as shown here. But high-grade metamorphic rocks are of course also granulites, and if you are increasing the pressure, then you are forming then eclogites and, yeah. So now next slide please, Holger. So now we have increasing metamorphic grade, yeah. We have at first diagenesis, then we have low-grade metamorphism, intermediate metamorphism, high-grade metamorphism. If we are subdividing this into phases, then we have green schists, amphibolites, granulites. A green schist, yeah, is a typical metamorphic rock formed under low-grade metamorphic condition, amphibolites forming under intermediate metamorphic conditions, and granulites under high-grade metamorphic conditions. So, and that is, for example, the changes in the mineral composition of a shale during metamorphism. Yeah, we are forming then a shale during metamorphism, that is then a calcium-rich rock. So under green schist phasous conditions, we have then a chloride, then we have a white mica, and this white mica is most commonly or mainly a muscovite. Then under intermediate metamorphic conditions, we have a biotite and the garnet. The garnet is also stable in granulites, but the garnet formed in amphibolites is more an iron-rich garnet. And in the granulites, the garnet becomes then more and more rich in magnesium because it must accommodate higher temperature conditions. And that's the same for the biotite. Under low-grade metamorphic conditions, you are forming an iron-rich biotite, whereas when you are increasing the the pressure and temperature conditions, then you are forming then a more magnesium-rich biotite. Then you have this small field from the staurolites. Then under intermediate conditions, you have a kyanite, which is an alumosilicate, and under high-grade metamorphic conditions, in the granulite phases, you are forming the alumosilicate silimanite. So and now we have this mineral assemblage, and that is a typical mineral assemblage for a shale during metamorphism. But now we have to talk about or think about what type of metamorphism is, and that is a regional metamorphic event. We are expecting here medium pressure, a PT pass along medium pressure and medium temperature conditions, yeah, in a collision zone, mainly a continent collision zone, yeah, because if it would be an subduction zone, then we would have a much steeper PT pass. That means high pressure conditions but low pressure, high pressure conditions but low temperature metamorphism. So and then we have also the plagioclase is present in all these rock types, and there we have a more sodium rich plagioclase, but I have to mention, of course, this plagioclase formed under granulite phasous condition contains then more calcium as this plagioclase on the left hand, which is formed under greenschist phasous condition. So now we have the same diagram again, but we are changing the bulk rock chemistry of the precursor. We have the change in the mineral composition of mafic rock during metamorphism. So under low-grade metamorphic condition or while during diagenesis, we have then so-called zeolites. Zeolites are very water-rich minerals. You know this from last year. In low-grade metamorphic conditions, we are talking about greenschist phasous conditions or green schist. And there we have the chloride present, which makes the green schist green, yeah. Then we have the epidote. Then we have amphibole, yeah, at low pressure, low temperature, low pressure conditions. We have a non-aluminium amphibole, and if we are increasing the pressure and temperature conditions, then our amphibole contains more and more aluminium, and this aluminium is replacing the silica. Then we have in the amphibolite phasous, we have then the garnet, yeah, in the garnet is stably under from the transition zone between the greenschist to the amphibolites, then into the granulites. So, and I mean the garnets formed in the amphibolite phasous, they contain then more iron, and those one in the granulites more magnesium. Then we have the pyroxenes. It depends if we can have there 2 pyroxene granulites. If the granulites are formed under lower pressure, yeah, then we have 2 pyroxene granulites, clinopyroxene, which is most commonly the end member diopside. So, and then we have an autopyroxene, which is then mostly an enstatite or a mixture between an enstatite and a ferrosilite. So, and the clinopyroxene is also a mixture between the end member diopside and Hedenbergite. So, and then in all these rock types, we have plagioclase present at low temperature conditions, sodium rich at high pressure and temperature conditions, calcium rich. So that is how the mineral assemblage changes with depending on the bulk rock chemistry of our metamorphic rocks, yeah. So in the bulk rock chemistry, that is controlled by the precursor of the metamorphic rock, yeah. It can be an aluminium rich metaphylitic rock, it can be a shale it can be ultramafic rock, it can be an aluminium-rich sediment like a metapilite. It can be a marl or anything, yeah, which undergoes then high-grade metamorphism, and then you are forming different minerals depending on the bulk rock chemistry from your precursor, and that has then a strong influence on the type of minerals which you are forming then in your metamorphic rock, additionally to the given pressure and temperature under which metamorphism took place. So now comparing these two diagrams, we have here on the left hand the changes in the mineral composition of the shales during metamorphism, and in diagram B we have the changes in the mineral composition of mafic rock during metamorphism, yeah. So, and then we have in table number C the metamorphic phases, yeah. We have the green schist, the amphibolite, the granulite, and the eclogite. So, and then we have the mineral produced from shale in the parent. So then we have there and the minerals produced from basalt in the parent. So then we have under green schist phaseous condition, we have in the shale parent we have muscovite, chlorite, quartz, albite. Whereas in the basalt parental rock we have albite, epidote, chloride. So then under amphibolite phaseous conditions in the parental shale rock we have muscovite, biotite, garnet, quartz, albite, staurolite, kyanite, sillimanite. And in contrast to that, in the parental basalt we have amphibole, plagioclase, and feldspar. So you can see here all the aluminium rocks all the aluminium rich minerals are missing, and that is just because in the basalt you have much lower aluminium concentration inside, and therefore you will not form that much aluminium bearing rocks afterwards. So under granulite phaseous condition in your parental shale rock you have garnet, sillimanite, albite, autoclase, quartz, biotite, whereas in the parental basalt you have calcium rich pyroxene, calcium rich plagioclase, feldspar, and so on. Yes, and there you have then also the pyroxenes and the garnets, yeah. I don't know why they have not written this here. So, and then under eclogite phaseous condition in the parental shale you have garnet, sodium rich pyroxene. That is then a sodium rich pyroxene is a jadate, for example, quartz, coesite, and kyanite, whereas in the parental basalt you have the sodium rich pyroxene, in this case that is an omphacite, and garnet, yeah. So, and in a sodium rich, in a typical eclogite which is derived from a basalt or from a gabbro, metamorphosed basalt or gabbro, you will never find plagioclase. You have your mineral assemblage consists of omphacite, which is the sodium rich pyroxene, and garnet. So now we have here the different geotherms, yeah. So we have here and the different phaseous fields in this metamorphic diagram with the flipped pressure and depth axis. So then, but we have here at very low pressures and relatively high temperatures, we have here the area of where contact metamorphism takes place. You are forming there rocks which we are calling hornfelds, and such a hornfels is very, very fine grained and does not show any schistosity or deformation textures because it was just heated up. So then we have this greenish path, yeah, that is then the condition beneath mountain belts, yeah, collision geotherm, and that goes then through the green schist over the amphibolite into the granulite fascias, and can then also go up into the eclogite fascias. So, and then we have the blue geotherm starting with the zeolites, going up into a subduction zone through the blue schist fields, through the field of the blue schists, and that is just where oceanic crust becomes subducted beneath a continental crust, and we are expecting high pressure conditions and relatively low temperature conditions. So, and then we have this yellow path, and that is where partial melting of the rock starts, yeah. So it depends then on the fluid composition in your rock, then partial melting will take place, and this partial melt will become removed from your rock and has then a different composition from the metamorphic precursor, as a different, and leaving also back a metamorphic rock with a different chemical composition again, because you are subtracting certain parts from your metamorphic precursor then by the formation of partial melt. So, and the metamorphic phases correspond to particular combinations of pressure and temperature. The pressure and temperature which I'm just talking to you now is now cutted away, but you have the pressure and temperature on your slide in the PowerPoint which I have uploaded on Moodle, so please recheck it. And can be used to indicate specific tectonic environments, yeah? So that has also been cutted away, so please feel free, open the PowerPoint which I have uploaded, and then you can watch it. So now I have some short questions for this chapter. You have mapped an area of metamorphic rocks, which you have done when you were in the field, such as the region in figure 6.9a, and have observed a series of metamorphic zones marked by north-south isogrades, running from sillimanite in the east to the chloride in the west, where metamorphic temperature higher in the east or west. So that is now a question which you should be able to answer easily. So which kind of pluton would produce the highest grade of metamorphism? A granitic intrusion, a granite intrusion 20 kilometer deep, or a gabbro intrusion at a depth of 5 kilometer, yeah? That you should also be able to answer very easily. So now number 5, plate tectonic and metamorphism. So metamorphism occurs only in or near to plate interiors, to divergent plate margins, to convergent plate margins, and at transform plate margins. So, and now we will check where this is. So here we have, for example, the first nice picture, and there we have a high pressure and high temperature metamorphism. At the beginning we are talking about low pressure, low temperature metamorphism at this point, yeah? At this point, and then we are going here and there, it comes back to the Earth's surface, and it comes back to the Earth's surface via isostasy. That means by weathering we are removing always parts from the surface. That is usually chemical weathering and mechanical weathering, yeah? And the highest degree of weathering can be produced by ice, yeah? If you have a glacier, can be remove huge blocks of rocks. So, but most common type of weathering, that is then the water, yeah? With water, you have rainfall, weather and alteration and weathering processes starting, and your rock types at the surface, they will just fall in pieces. And then all these fine-grained particles becoming then transported to the ocean and deposited at the sea. You know this from last semester, yeah? So in this blue path is then a typical path on a subduction zone, yeah, where we have at the beginning low pressure and low temperature. So, and therefore we have a tectonic transport, and that moves rocks through different pressure and temperature zones. So, and the pressure increases with the depth, and the temperature also increases with the depth. So, and therefore we can subdivide low pressure, low temperature metamorphism, and we have also zones, of course. Yes, and then transport them back to the shallow crust or surface, and that is by isostasy and weathering. And then you, as a geologist, you can walk around on the surface and sample all these rocks, or you are bringing them back by a volcanic eruption or a kimberlite, yeah? So, and here when we are increasing the depth, then we are increasing then the pressure and the temperature conditions. So, and therefore we can construct metamorphic pressure and temperature paths. So, and that gives us the history of burial and exhumation. And we are talking about prograde and retrograde passes. So here we have now a thin section, yeah? So, and this thin section shows the first one shows us a garnet gneiss, yeah? And you can see all these reddish bubbles inside. These are garnet crystals, and such a garnet crystal has to grow. So what is written here: during metamorphism, a garnet crystal grows, and the composition of the growing crystal changes as the temperature and pressure around change. So, and then you have here these pressure shadows, yeah, you can see this here, and then you have here these garnet granoblasts, yeah, and we are calling these granoblasts because the garnet does not show any direction. So, and if we are constructing a PD path, then we are using the chemical composition of our minerals. That is one thing. So, and therefore when the garnet starts to grow in the center, which is here seen by number 1, the garnet has a different mineral chemical composition at the place number or spot number 1 compared to number 2, yeah? So the composition of the crystal can be plotted on the PT path as it grows from 1 in its center to 2 at its edge, yeah, and there we have the growth zoning in garnets, yeah. Not only garnets has this, but the garnet is a very suitable mineral to for calculating a PT path. So and therefore we are having here the prograde PT pass. We have here as in this example we have a aluminium rich sedimentary rock as a precursor. Therefore we are forming here a slate, yeah. So and then we are metamorphic conditions increase on the prograde pass, yeah. On the prograde pass we will then form a phyllite. So then we have here the garnet, the composition of the garnet here at place number 1 at about 520 degrees Celsius and 7.5 kilobar. So and then the garnet crystal grows and grows till we are reaching temperatures of 900 degrees Celsius and pressure conditions of about 8.2 kilobars, and then we are sending the whole rock assemblage back to the surface along the retrograde PT path. So in this prograde PT path as well as the retrograde PT path, as the peak metamorphic conditions can be calculated using the different mineral assemblages which has been formed at different pressure and temperature conditions. So that means you can analyze all this mineral composition from your rock forming minerals. You can check them under the microscope if they are in equilibrium with each other or not, and then you can calculate such an PT path, and that is actually the main thing what I'm doing the whole day, and that is a lot of fun. So and when we have calculated the PT path, then we can reconstruct the metamorphic history of our sampled rocks. So we have here, for example, this reddish PT path. This reddish PT path, we have here a prograde, very steep prograde PT path, and that is typical for low temperature, high pressure metamorphism within a subduction zone. And that we have here the subduction of an oceanic lithosphere beneath a continental lithosphere. So and there we are expecting then high, we are expecting then a PT path, and very steep PT path showing low pressure, low temperature condition but high, low temperature condition but high pressure condition, like this reddish PT path here. Here we have the prograde path from this point to this point. That is then from here to here, yeah. So then we are bringing our rock sample back to the surface. That is then the retrograde path from here to here. And here we have peak metamorphic conditions, yeah. That is this point here, peak metamorphism, prograde path, retrograde path, yeah. I don't know why this always flips. So and of course we have then in these different settings, we have different rocks. And these different rocks has a different bulk rock chemistry, depending if they are formerly basalts or gabbros, if they are formerly peridotites, or if they are formerly sediments or shelves or whatever, yeah. So now we're expecting here a second picture. Ah, Gott, zack! A second picture here, and that is typical for this PT path. Yes, here we have more a collision zone and a multiple thrust here. So, and here we have a collision zone between this continental landmass and this continental landmass. We have here from here to here the prograde path, that is from here to here the prograde path. Here we have again peak metamorphic condition, and here we have the retrograde path with the examination to the Earth's surface, yeah? To the Earth's surface, that is the retrograde path. So, and then we have here the suture zone. Here we have deformation and metamorphosed shallow and deep ocean sediments. And here we have our continental crust. So on this side we have here the melange zone with the ophiolites, yeah. That is the abducted, highly hydrated peridotites. And here also again the continental crust, and here the trench. So, and then just check these figures again, go through them, and please load down the PowerPoints which I have loaded up on the internet, that you have the full text from below. So, and these are the different ways how different PT passes can be related to different geotectonic settings. Here we have low temperature, high pressure metamorphism within the subduction zone. And here we have high temperature, high pressure metamorphism within a mountain belt, yeah? So number 5, so we have then the next points which I have to mention to you. First point, rapid erosion, that means exhumination rates of mountains, ranges, show a relationship between what you are thinking about, tectonics and orogeny, climate. Yeah, of course, if you have a lot of rain, then you will, weathering will start much faster, will take place much faster, and therefore the erosion rate is higher. So in the climate, of course, if you are in a very humid area, then the erosion will also take place much faster. So, and that controls the flow of metamorphic rocks at the surface. Then we have another thought for the thought questions for this chapter. Draw a sketch showing how seafloor metamorphism might take place. Yeah, you can do this. It should now be an easy question for you. So then, next thing, subduction zones are generally characterized by high pressure, low temperature metamorphism. In contrast, continent-continent collision zones are marked by moderate pressure, high temperature metamorphism. Which type of plate boundary has a higher geothermal gradient? You should also be able to answer this question easily and explain why you are coming to your conclusion. So now we have at the end key and terms and concept for these questions. For this chapter, you see we are now at the end for this chapter, and I have now also talked for 43 minutes, yeah, when I have read through the key terms and concepts. Then we have our 50 minutes, you have the next class, and we will continue with the next classes by Wednesday. So, key terms and concepts. We are starting with A and going then just through the whole alphabet, how in the same way as we have done it in the last 2 weeks. Amphibolites, blue schists, we have discussed the burial metamorphism, the contact metamorphism, the eclogites, the exhumination, the foliated rock types, the foliation itself, the gneiss, the granoblastic rock, yeah, the granulite, the green schist, the greenstone. We discussed, or I told you also what we understand under high-grade metamorphism, under an hornfels, under a marble, or what a melange is, what metamorphic phases do we have, what we understand under metasomatism, what's a migmatite is, and phyllite, and porphyroblast, and quartzite, what we understand under regional scale metamorphism, what a schist is, what we understand under seafloor metamorphism, under shock metamorphism, what a slate is, what is meant by the stress, what is meant by a suture. So then we talked about ultra high pressure metamorphism, about zeolite, and that was it for today. So, and I will upload for you the next class on Wednesday. Yes, see you then on Wednesday, and now you can work on all these short questions belonging to the metamorphic rocks and handing this in by Friday or by Sunday. Yeah? Okay, see you then. Bye.